Morning, everyone. Welcome to Chapter 2. It is definitely fire season here in Reno, as you can tell by all the smoke behind me. We're going to talk about chemistry, and what's interesting is that fire is a chemical reaction. The rapid combination of oxygen and hydrocarbons produces water, CO2, and heat. In this chapter, we're going to talk about the atoms and molecules that make up chemical reactions and how that all works. Chemistry is the basis of life. All life on Earth is carbon-based, because carbon can form 4 bonds, thus allowing for an incredible array of molecules and structures. Carbon is an atom. Atoms are the basic units of matter. Elements are substances that are made up of a single type of atom. The oxygen that you breathe is an element consisting of 2 oxygen atoms. Nitrogen gas is an element consisting of 2 nitrogen atoms. In contrast, a compound is a substance that is made of different kinds of atoms. For example, water is a compound that is made from 1 oxygen atom and 2 hydrogen atoms, and carbon dioxide is made of 1 carbon atom and 2 oxygen atoms. Essential elements are what are required for life. These include oxygen, carbon, hydrogen, as well as nitrogen, calcium, potassium, and others. In total, human beings require 25 essential elements to survive. Trace elements are still required, but an organism only needs a tiny amount of them to survive. This is why table salt generally has iodine in it. Iodine is a trace element, and it can be lacking in the modern diet. People used to suffer from goiter because their thyroid gland did not have enough iodine. Atoms are the smallest unit of an element that still retain the properties of that element. If you cut an atom down, you get smaller particles, but they act very differently than the atom you cut them from. These particles are electrons, protons, and neutrons, and they each have their own subatomic properties. Protons are positively charged, and electrons are negatively charged. If an atom has less electrons than protons, it becomes positively charged. On the other hand, if it has more electrons than protons, it becomes negatively charged. Neutrons do not have a charge. When an atom is charged, we call it an ion, but we will talk more about ions later. Neutrons are not charged, and adding or removing them changes the stability of an atom, but it doesn't add a charge. Atoms with too many neutrons can be radioactive, like carbon-14, which is used in modern methods to date the age of rocks. An uncharged atom has a nucleus, which is a tightly packed ball of protons and neutrons. Electrons form a cloud around the nucleus. An uncharged atom has the same number of electrons as it does protons, and as we saw, neutrons don't affect the charge. The identity of an atom is defined by the amount of protons in its nucleus. For example, carbon has 6 protons. If we take away or add protons, it's no longer carbon. An atom with 7 protons is called nitrogen, and 8 protons is called oxygen. The number of protons in an atom is called the atomic number. So an atom with an atomic number of 6 is always carbon. However, because the nucleus also contains neutrons, they contribute to the total mass, or what we call the mass number. If we add up the mass of all the protons and all the neutrons in a single atom, we get the mass number. Because electrons don't add significant weight to an atom, we say that the mass of the atom is just the weight of the particles in the nucleus. The shorthand notation for writing this is to use the atomic symbol. All atoms have an atomic symbol. This is the atomic symbol for sodium. The symbol doesn't always match the English name for an atom. So once we have our atomic symbol, then we add to that the mass number is a superscript and the atomic number is a subscript, like this. Let's look at what we know about the atom. Using sodium as an example. Sodium has an atomic number of 11, which means it has 11 protons in its nucleus. However, the total mass number of sodium is 23. We can figure out how many neutrons are in the nucleus of sodium by subtracting the number of protons, 11, from the total mass of 23. and we get 12 neutrons. The mass number minus the atomic number equals the total number of neutrons. Now is a good time to introduce the periodic table. The periodic table of elements can tell us a lot about the properties of an atom very quickly if we know what to look for. As we learn more about atoms and chemical bonding, we will refer back to this table and see how it can help us make predictions about chemical bonds and atomic properties, such as electronegativity. This chemical makeup is just one part of the signature of Earth's organic heritage, a heritage that is shared by all life on this planet. Atoms each have a nucleus that contains a number of protons and neutrons, which are surrounded by orbiting electrons. The protons of the nucleus are positively charged, and the electrons in orbit are negatively charged. The fact that they have opposite charges means that they can attract each other. However, electrons don't just dive down and stick to the protons. They orbit, and like a space shuttle orbiting the Earth, they have energy that allows them to partially fight the attractive force of their charges. For a space shuttle to resist the pull of gravity, and stay in orbit, it requires the use of energy in the form of fuel and rocket boosters. The thrusters use this fuel to give the shuttle motion. Energy of motion is called kinetic energy. The more kinetic energy the space shuttle has, the farther away from Earth it will orbit. Electrons act something like this. While it is true that electrons orbit the atom, they do not do so exactly like a space shuttle. In fact, electrons are a complicated thing to talk about, and it's not necessary to understand all the physics that describe them. Here, it is important to know that electrons have energy, similar to the kinetic energy of the space shuttle, and the amount of energy that they have keeps them in a specific orbit. And like the shuttle, the more energy they have, the farther out they will orbit. What's interesting about electrons is that they are quantized, which means that they can only orbit at specific distances from the nucleus, according to the amount of energy they have. We see here that electrons can only occupy specific orbits, or shells. If you were to measure the energy of electrons in an atom, you would always get back a value that corresponds to an orbit in one of these shells. If you add energy to an electron, it can only absorb the exact amount of energy that will raise it to one of these higher shells. So electrons orbit an atom in discrete shells according to their energy level. Are you ready to learn some quantum mechanics? Actually, it's not as hard as that sounds, but electrons do weird things, and quantum mechanics is the language of the weird. Because of the nature of quantum mechanics, there is a limited number of electrons that can orbit an atom at each shell. Atoms have a number of shells based on the number of protons, or their atomic number. This makes sense. Hydrogen has an atomic number of 1, so it only has 1 proton and 1 electron that lives in the lowest electron shell. Carbon has an atomic number of 6, so it has 6 electrons that take up 2 shells. For us, it is important to know that the very lowest shell only ever holds 2 electrons. However, all the shells that come after that can hold 8 electrons each. Electrons fill the shells starting at the lowest energy and move up. Thus, hydrogen's 1 electron is in the lowest shell. However, lithium has 3 electrons and 2 electron shells. The first 2 electrons fill up the lowest shell, and the final electron takes its place in the second shell all by itself. We mentioned that carbon has 6 electrons in 2 shells. The first 2 electrons occupy the lowest shell, and the 4 remaining all take up residence in that second shell. Because the second, and third, and fourth, and so on, shell can take 8 electrons, 4 more electrons need to be added before the next electron can start hanging out in the third shell. Here's a diagram of how the electron shells are filled in atoms in the first few rows of the periodic table. Notice all the atoms have no more than 2 electrons in their lowest energy shell, and the rest of the shells stop at 8. Earlier, I said that carbon had 4 electrons in the second shell, and lithium had 1 in its second shell. These electrons are what we call valence electrons. Valence electrons are all the electrons that are hanging out in the highest energy shell that a particular atom has. So carbon has 4 valence electrons, and lithium only has 1. How many valence electrons does fluorine have? If you said 7, then you were correct. Notice something interesting about the periodic table. That's right, carbon has 4 valence electrons, and so does silicon. In fact, if we look at any atom, all the atoms above and below it will have the same number of valence electrons. Helium is an exception, but we will discuss that in a minute. Now, we are ready to start looking at the super exciting stuff. Chemical bonds. Chemical bonds are what make life possible. Chemical bonds are the result of the way electron shells are arranged and the way electrons behave, or misbehave as they are prone to do. When 2 or more atoms come together in a single structure, they are called a molecule. Molecules have unique and interesting emergent properties because of the atoms that make them up, as well as the way those atoms are arranged. So, what is the key to chemical bonding? What property of atoms makes bonds not only possible, but guaranteed? It is the valence electron shell that provides the bonding nature of atoms. You see, atoms want their outermost valence electron shell to be filled up, meaning for hydrogen and helium, they both want 2 electrons, but for all other atoms, they want 8 electrons filling up their outer shell. However, most of them lack the protons to do that alone. If we look over at the far right of the periodic table, we see that some atoms do have full outer shells. They have 8 electrons in the outermost electron shell, and as a consequence, they are full up and not very reactive. The last column is referred to as the noble gases. However, all the other atoms are missing at least 1 electron in their outer electron shell, and therefore are reactive in some way. There are 4 kinds of chemical bonds: covalent bonds, ionic bonds, hydrogen bonds, and van der Waals forces. These are arranged here in the order of strongest to weakest. However, even weak bonds can be powerful enough if enough of them are present. The first 2 kinds of bonds are directly related to valence electrons, and the second 2 we'll discuss more later on. Covalent bonds are a way for atoms to fill up their valence electron shells through sharing. If your mother always told you, you need to share, she would be proud of you because most of the atoms in your body are sharing their electrons all the time. Let's take hydrogen to start with as a simple example. Hydrogen has 1 electron, and it is alone in the lowest electron shell, which we remember can hold up to 2. If 2 hydrogen atoms come together, now they are sharing their 1 electron, and both have 2. Thus, their shells are complete and they are happy. Hydrogen atoms form what is called a single bond. That means that each atom is only sharing 1 electron with the other. However, let's look at a more complicated case: oxygen. Oxygen has 6 valence electrons in its outermost shell. That means what it would really like to do is get 2 more electrons in that shell to make the 8 that would fill it up. When 2 oxygen atoms are close together, they can each share 2 of their electrons with the other. This gives them both 8 electrons in their shared shells. This is referred to as a double bond, because each atom of oxygen is sharing 2 electrons. It is important that we talk about carbon here. It was mentioned in a previous video that carbon is the basis of all life because it can form 4 bonds. And finally, we see why. Carbon has 4 valence electrons. That means that it needs 4 other electrons to be shared with it. So, we can imagine that since hydrogen atoms need 1 valence electron to be happy, that 4 hydrogen atoms could each share 1 with carbon. That way, carbon has 8 electrons in its shared outer shell, and each hydrogen atom is sharing 1 electron with the carbon, so they each have 2 electrons in their shared shells. The molecule that results from this bonding is called methane. Carbon has formed 4 single bonds with 4 different hydrogens. However, carbon can also form single bonds with itself and create ever more elaborate structures. These are the structures upon which all life is built.